Alright, so this is a continuation of Unit 8, and now we're going to talk about different types of reactions and how we can classify reactions. Okay, well there's two different ways that we can classify reactions. The first way is by type. There are generally two types of reactions. Redox reactions, which is shortened from oxidation reduction. An oxidation reduction reaction is where an electron transfers from one substance to another. And then there's non-redox reactions, and there's actually two subcategories of that. There's precipitation reactions, where ions stick together to form solids, ions that are dissolved in water and then can't stay dissolved anymore and form a solid. And then there's acid-base reactions, and this is a type of reaction where a hydrogen ion transfers from one substance to another. In this chapter, we're going to talk about redox reactions, we're going to talk about precipitation reactions, and then acid-base reactions will be a future unit, I think 11. So, another way that you can classify reactions is by the mechanism type, so what's actually happening during the reaction. There are three basic ones: decomposition, combination, and then displacement, or sometimes you can also hear it called replacement. And then displacement, there's two types, either single or double. Alright, so let's start with decomposition reaction. A decomposition reaction, just like the name implies, is something that decomposes. And so you can always tell a decomposition reaction when you have one reactant and then it's broken down into two or more products. Decomposition reactions can be either redox or non-redox reactions. As you can see here, the general form is just where you have one reactant breaking down into two or more products. An example of a redox decomposition you can see here, 2HI decomposing to H2 plus I2. An example of non-redox decomposition is H2CO3, which is carbonic acid. That's the acid that is in your soda, and it breaks down into CO2, carbon dioxide, and water. So that's what's happening when you're drinking your soda. Just by the way, you don't need to particularly remember what's redox and non-redox. When we talk about redox reactions, I'll kind of tell you this is a redox reaction and then different things about that. But I'm just giving you examples for right now. So here's a pictorial representation of a decomposition reaction, and you can see we only have one reactant, one thing. It doesn't really react with anything, but it breaks apart into two or more products. So this reaction is H2O2 peroxide. If you have peroxide sitting around in your medicine cabinet, this actually happens over time, where the peroxide will decompose into water and oxygen. And then you can see another example down below. If you can take water, actually it doesn't just happen, you have to make it happen by putting energy into it. But if you take water, it can decompose down into its two elements, hydrogen and oxygen. You might want to watch this little YouTube video before you go on. Alright, a combination reaction, again, just like the name implies, is a reaction where two or more substances react to form a single compound. So they're combining to form one product. So you can recognize a combination reaction if there's only one product. And again, combination reactions can be either redox or non-redox reactions. So you can see the general form, two things, two reactants add together to form one product. That's a combination reaction. An example of a redox combination reaction is where sulfur combines with oxygen to form sulfur dioxide. That rotten egg smell. An example of a non-redox combination reaction is, you can see here, N2O5, dinitrogen pentoxide, reacting with water to give us nitric acid, HNO3. Here's a pictorial representation. So you've got two different things forming to combine one product. Alright, and then you can see another example down there. A single replacement reaction is one that is always a redox reaction. when you see, if you could see the general form here, you can see that you've got A plus BX. So in the reactants, A is by itself and B is combined with X. And then in the products, B is by itself and A has combined with X. So it's sort of like they've swapped places. A has replaced B with X. So it's a single replacement because one thing has replaced one other thing. An example of a single replacement reaction, you can see there on the bottom, is zinc reacting with copper sulfate to give us copper metal and zinc sulfate. Earlier in the earlier PowerPoint, we saw one where we stuck some copper wire into silver and we got silver metal. I think that's on the. So this is a pictorial representation of a single placement reaction, and you can see H2 on the left by itself, copper with the oxygen on the left, and then on the right of the arrow, copper by itself and the hydrogen with the oxygen. And so a single replacement reaction. Another example, copper reacting with silver nitrate. This is the one that I was just talking about. There's a picture on the second slide where the copper goes into solution and the silver precipitates or forms on the copper wire. So copper by itself, silver nitrate, silver with the nitrate, and then on the right side, silver by itself, copper with the nitrate. You might want to watch this video. It doesn't work in my narration. You can hear it, but you can't see the picture. So you might want to try looking at that and then coming back. Okay. A combustion reaction, this wasn't listed earlier, but a combustion reaction is a special type of single replacement reaction. And I like to highlight it because combustion reactions are so prevalent. Usually a combustion reaction occurs when you have a hydrocarbon. A hydrocarbon is just a compound that has only carbons and hydrogens. And a hydrocarbon reacts with oxygen to produce carbon dioxide and water. So an example of a combustion reaction that we actually talked about earlier was CH4, methane. When methane reacts with oxygen, we get carbon dioxide and water. The gasoline in your car, again, gasoline is a type of hydrocarbon. Octane has 6 carbons and 14 hydrogen. That is one. It's a hydrocarbon that will combust to give CO2 and H2O. And also, we'll talk about this later, but it also gives off heat. Butane, propane, any of those are hydrocarbons that when they react with oxygen form carbon dioxide and water, which is a combustion reaction. Also, when you break down sugar or other nutrients in the body, that's also considered a combustion reaction. So here you can see C6H12O6, which is glucose or fructose, it's either one. When it reacts with oxygen, again, we get CO2 and H2O. So that's a type of single replacement reaction. All right, a double replacement reaction, as the name would imply, is where two things replace each other. And double replacement reactions are never redox reactions. These are actually either precipitation or acid-base reactions. So in a typical reaction, two dissolved compounds will react, and what they do is exchange partners. So if you look at the general equation, you can see that AX reacts with BY. So A is with X, B is with Y. And then on the product side, B is with X and A is with Y. So two things have replaced each other. The A and the B have replaced each other with the X and the Y. So a double replacement has two things that have replaced each other. You can see on the bottom an example of a double replacement reaction. If we take barium nitrate, sodium sulfide, if we react those together, the barium sulfide forms a precipitate. You can see the S there means solid, and then NaNO3. So you can see the Ba was with the NO3, and then in the products the Ba is with the S. In the reactants the Na was with the S, and in the products the Na was with the NO3. So it's sort of swapped partners. All right, here's a pictorial representation of a double replacement reaction. So NaOH, the OH stays together, but the H from the F combines with the OH, and the Na and the F combined, and so we have a double replacement. All right, let's do a few examples. So classify the following reactions as either decomposition, combination, single replacement, or double replacement. All right, so the first one, 2HI produces H2 and I2. I'll give you a minute to think about it. All right, well, the main thing to notice here is that we only have one reactant. When one reactant breaks apart, then that is decomposition. All right, and NaCl plus AgNO3 produces AgCl and NaNO3. All right, well, notice that there are four different types of atoms there, elements, and this is one where they have swapped places. So the Na is now with the NO3 and the Ag is now with the Cl. That is a double displacement or double replacement. The third one, 4P plus 5O2 gives us 2P2O5. Again, the thing to notice here is that there's only one product. One product indicates a combination reaction. H2O2 breaks down to give me H2O and O2. Actually, this one was an example earlier. Again, there's only one reactant, and so this has to be decomposition. Finally, NaI plus Cl2 to give NaCl plus I2. In this case, the Cl is by itself on the left, the I is by itself on the right, and the Na has swapped from the I to the Cl, and so that is a single replacement or single displacement reaction. A few more examples. Okay, so classify each of these. NaOH plus HCl gives us NaCl plus H2O. That is a double replacement. The OH and the H have combined on the products, and the Na and the Cl have combined, swapped places. Mg plus O2 to give us MgO. Again, we see one product, which is combination. Na2CO3 gives us Na2O plus CO2. That, again, one reactant means that it's decomposition. And then Mg plus 2HCl gives us MgCl2 and H2. So this one is a single replacement because the Mg has replaced the H with the Cl. So one thing has replaced another. All right, I hope that you can look back at these and make sure you can identify the types of reactions. All right, so we have our types by mechanism. So double replacement, single replacement, decomposition, combination. And as I mentioned earlier, we can have non-redox reactions, which can either be classified under precipitation or acid-base. And as I mentioned, you can have combination, double replacement, or decomposition. And then redox, which is, again, oxidation reduction, you can have combination, single replacement, or decomposition. What we've got next is redox reactions. So I'm going to talk about that. This actually can get very complicated, and we're not going to get really complicated. You'll see on the right here there's something about increasing oxidation number, decreasing oxidation number. We're not going to be calculating oxidation numbers in this course, and so you can kind of omit that. But I wanted to put that in there because you may come across that sometime, and oxidation numbers are one way of determining a redox reaction. Anyway, the word redox, as I mentioned earlier, is a combination of the two words reduction and oxidation. All right, so what is reduction? Let's step back. A redox reaction then is where an electron is transferred from one compound to another. So here are the main definitions. Oxidation means something that has lost an electron, and reduction is something that gains electrons. So when something has gained an electron, that is reduction. When something has lost an electron, that is oxidation. An important thing to remember is that they have to combine. You have to have both of them in order for a redox reaction to take place. So you have to have oxidation and you have to have reduction, because the electrons have to have somewhere to come from and somewhere to go to. A little mnemonic to remember oxidation and reduction. Leo the lion says GR. Oxidation means loss of electrons. Loss of electrons is oxidation. Gain of electrons is reduction. Sometimes I've also seen people use the mnemonic oil rig. Oxidation is loss. Reduction is gain. Oil rig. There are actually some other meanings for oxidation. So the literal definition, loss of electrons. But as we'll see in the next few slides, oxidation can also mean to combine with oxygen, which I imagine that's where the word came from. It can also mean to lose hydrogen. Of course, it can mean to lose electrons. And then, as I said earlier, it can mean to increase oxidation number. Well, we're not going to really worry about that one. Reduction, then, is the opposite. You can think of reduction as losing oxygen, combining or adding hydrogen, or to gain electrons, or to decrease oxidation number. All right, so like I said, we're not going to be dealing with calculating oxidation numbers in this course. We'll use the other definitions to help determine what's being oxidized and what's. So let's look at an example of a redox reaction. All right, one thing that I just want to point out, that there are actually negative ions present in this reaction, but I just didn't write them in there because they don't really take part in the reaction, and it would just complicate things. So anyway, here we can see that we have zinc solid, which is the metal, and we have copper ions, copper 2+ ions. So that means they're dissolved in solution. That's, you see the AQ. Well, if you put zinc metal and copper ions together, they will react, and the zinc will become an ion, zinc 2+, and the copper will become a solid metal, similar to the Ag and the copper that we saw earlier in the picture. So what's actually happening? Let's pull this apart into two parts. So the zinc is actually losing electrons, and we've seen this before back in chapter or unit 3, I think 3 or 4, 4, where maybe it was 5. Sorry. Anyway, where elements lost their electrons. I think that was unit 5. So when zinc loses electrons, in this case zinc loses 2 electrons to become positive, that is oxidation, the definition, loss of electrons. So zinc has lost electrons to become the zinc 2+. Copper, on the other hand, starts out as a 2+ and becomes copper 0, neutral. So copper has gained 2 electrons, and so copper is being reduced, or copper 2+ to copper is called reduction. So zinc becoming zinc 2+ is oxidation, and copper 2+ becoming copper metal is reduction. Again, oxidation and reduction must occur at the same time. So if we look at it from this point of view, we can see that zinc has been oxidized and copper has been reduced, or reduction. Okay, so this is one way that you can identify an oxidation reduction, is you can look to see, now the zinc has become more positive, which means it lost electrons, so that's oxidation, and the copper has become less positive, or more negative. Even though it's 0, it's still becoming more negative from positive 2, and so it has gained electrons, and so that is reduction. So if I give you an example like that, you'll need to identify what's being oxidized and what's being reduced in a reaction. So there are 2 simple ways to identify both parts. The one that I just told you, which means following the charges. So if you follow the charges, if it becomes more positive, that means oxidation. And if it becomes more negative, or if there's a reduction in the charge, then it is reduction. So you can see now where the name reduction comes from. There's a reduction in the charge. So zinc becoming more positive, increase in the charge is oxidation, and then a decrease in charge is reduction. So that's one way. If you've got charges, you can follow the charges and see what's going on. That you can determine what's being oxidized and what's being reduced is to follow the oxygen or the hydrogen. So remember, oxidation means to combine with oxygen. And so usually what you can do is you can look at the element that has increased the number of oxygens attached. And since it's also defined as a loss of hydrogen, sometimes you can look to see what element has decreased the number of H's, and it's usually the same element. And then since reduction is defined as a loss of electron or gain of hydrogen, then we'll look for the element that has decreased the number of O's or increased the number of H's. Okay, so if we look at this example, carbon on the left is attached to hydrogen. On the right, carbon is attached to oxygen. So what's happened? Carbon has lost the hydrogen and has gained the oxygen. So if it gains oxygen, that is oxidation. The oxygen molecule, and this might be a little bit harder to see, but notice that there's two of them, O2, and then on the right-hand side, there's only one of them, so the oxygen has actually reduced. It lost one of its O's and gained two hydrogens, so the oxygen has been reduced. And just a little hint, you always want to look at the reactants. So start with the reactants. Which reactant has been oxidized and which reactant has been reduced? Okay, and also if you figure out which one's been oxidized, it's the other one that has to be reduced. So sometimes it's not as hard as it looks. So again, CH4, and remember I said that this is also a combustion reaction, which is a redox reaction, and a single replacement reaction as well. Okay, so you can either follow the charges or follow the oxygen. So let's do a few examples. All right, the first one, Mg plus Cl2 to give Mg2 plus 2Cl negative. Well, since there's no hydrogen or oxygen in there, I guess we can't follow the hydrogen or oxygen, but we can follow the charges. So if you notice, Mg goes to Mg2 plus. So it has increased its charge. So that would be oxidation. Chlorine has gone from 0 to -2. Since that's a decrease in charge, that is a reduction. All right, how about the next one? Okay, so H2 plus 2Fe3 plus gives us 2Fe2 plus 2H plus. Again, well, there is hydrogen, but there's no oxygen, and the hydrogen stays separate. So we're going to follow the charges again. So hydrogen on the left has no charge, so that's 0. Hydrogen on the right has a +1. So if hydrogen has increased its charge, then that means it's oxidation. Hydrogen has been oxidized. The iron, you can see, is going from +3 to +2. So even though it's still positive, it's still going down. It's becoming more negative. It's decreasing or reducing the charge. So that has to be reduction. All right, finally the last one. Now you can see that there are no charges, but we do have oxygen, so we can follow the oxygen. So if we look on the left, the Fe is with the oxygen, and on the right, it's without the oxygen. So if something loses oxygen, then that is reduction. Oops, I got them backwards. So and then let's look at that. The carbon has gone from no oxygen to having oxygen, so that is oxidation. So carbon has gained the oxygen, oxidation, and iron has lost the oxygen, and so that is reduction. All right, just a few other little things just to tie up with oxidation and reduction. Sometimes you'll hear these terms, and on a test, I'm not going to ask you this. I'm just going to stick with what's being oxidized, what's being reduced. But out in the world, you often hear these other terms, and so I wanted to introduce them to you. The substance that is being oxidized during a reaction is often called the reducing agent. You know, it sounds kind of backwards, but if you think about the word agent, it means the thing that allows something else to be reduced. So if something's oxidized, it's allowing, or it's an agent to allow something else to be reduced. So something that is oxidized is called the reducing agent. And then on the flip side, if something is reduced, it can also be called an oxidizing agent because it allows oxidation to happen. So they're just the opposite of each other. So if you stick the word agent after it, just remember that it's the opposite of what it is. So an oxidizing agent is something that's reduced, which means it gains electrons or decreases its oxidation number, or becomes more negative in its charge. And then a reducing agent is actually something that becomes oxidized, loses electrons, and increases its charge. So it becomes more positive. So just something to keep in mind if you hear those terms. All right, so in each problem, let's determine what is the oxidizing agent and what is the reducing agent. So we saw before that carbon is losing hydrogen and gaining oxygen. So carbon is being oxidized, means carbon is the reducing agent. Oxygen, we saw earlier, is being reduced, and so it is the oxidizing agent. And then the second one, which we saw before, we saw that magnesium is becoming more positive, which means it is being oxidized. So magnesium is the reducing agent. And then the chlorine, which is becoming more negative, gaining electrons, is being reduced, and so it is the oxidizing agent. Okay, I hope that makes sense for you. All right. Okay, so finally, let's just look at a few examples of redox reactions. These are very prevalent in our everyday life, and so I just wanted to give you some examples. So as I said earlier, combustion, like gasoline or methane or butane or propane, reacting with oxygen to give us carbon dioxide and water is a type of redox reaction. Oxygen is reduced and the gasoline and the carbon is oxidized. Respiration, where we have sugar reacting with oxygen to give us, this is what gives us our energy in our body. The sugar is oxidized and the oxygen is reduced. Resting, if you take some iron furniture and it's out in the damp weather or an iron nail or something like that and react it with oxygen, eventually you'll get rust. Again, the oxygen, that's why it's called an oxidation reaction often, is that oxygen's involved. The oxygen is reduced, the iron is oxidized. Bleaching is an oxidation reduction reaction. And then batteries. So if you look at the first line, zinc plus 2OH negative to give us zinc oxide and water, also produces 2 electrons. So the loss of electrons is oxidation. So, and then the second line, 2MnO2 plus H2O plus 2 electrons is reduction. And so what happens in a battery is it's got 2 different compartments, and in one compartment you've got the oxidation happening, and in the other compartment you have the reduction reaction, and the electrons flow from one compartment to another, and as it does, it kind of flows through the whatever you're trying to charge up, and then comes back on the other side, and so the electrons actually flow through the battery, and that's what gives us our power. So anyway, this is the second part of our Unit 8 on reactions. The next segment will cover precipitation reactions. All right, we'll see you later.